Okay, so right now we're going to be looking at a motionless box on a ramp. We're going to construct a quantitative force diagram for this 10 kilogram box. When we're drawing a quantitative force diagram, we start off by drawing a qualitative force diagram. Then after that, we apply the quantities to it. So the first force that I'm going to draw that is acting on this motionless box is going to be the force of gravity pointing straight down. So we have a force of gravity on the box by the Earth. Then after that, we see any other non-contact forces for any of those forces that are acting on this box. The other types of non-contact forces are the magnetic force and the electric force, neither of which would be applied here. So we need to see which forces are crossing that boundary. We have that force of gravity that is pointing straight down, of course, but after that, we just need to see what is touching it. This thing is on the ramp, so the ramp itself is touching it. We have this as the surface here. It is pushing upwards with that normal force, and it is going to be resisting the motion with a force of friction. So that's what I'm going to include on my actual force diagram. I'm going to have an upward force normal that's upward not in relation to the force of gravity, but in relation to the surface of the ramp. So force normal on the box by the ramp. Then I have a force of friction on the box by the ramp. Nothing else is touching the box, so nothing else can be exerting a force on the box. So when I have it this way, these do not fall directly on the x or the y axis, so I need to apply my own x and y axis along with the coordinate system of the motion of the box. If I set it up with the motion of the box where my x-axis aligns with the ramp, that means the force of friction is on the x-axis and the force normal is on the y. So I need to break up the force of gravity into its horizontal and vertical components. So the force of gravity would pull this box down and to the left. So I'm going to have that small leftward force of gravity horizontal to the ramp, and I'm going to have that force of gravity perpendicular or on my y-axis of the graph. I'm drawing those to scale with my force of gravity, so essentially it could end up looking like a triangle. Now, when I want to quantify my force of gravity, that's the only way that we actually know how to directly quantify a force. The force of gravity is quantified with 9.8 newtons of force for every kilogram of mass multiplied by the mass of the object. The mass of this object is 10 kilograms, so the force of gravity of the box itself is going to be 98 newtons. Our kilograms would end up canceling out. But right now, I need to ultimately try to figure out how much of that 98 newtons is broken up into the horizontal component, how much is in the vertical component, because I need to quantify the rest of these forces. Now, this is one of the reasons why when we write the sum of our forces equation, the way that we do. Actually, I think I might write that down closer to the bottom of this. Our sum of the forces equations. We want to make sure that we are writing it in a way that accounts for all of our forces. I know that along the x-axis, the force should be 0, because there's no motion of this box, it's at rest, and it's continuing to be at rest. I have the force of gravity horizontally, and I have the force of friction horizontally. I'm going to say that to the right is positive, that makes that my force of friction positive, and to the left is negative, that makes my force of gravity dash x negative. I can set the same thing for my sum of the forces vertically. Overall, it should be 0. It should be balanced out. I have that force normal and that force of gravity dash y that fall on my y-axis. I'm going to say up is positive and down is negative. When I have it set up this way, it really does allow me to say that the size of these two forces should be equivalent, and the size of these two forces should be equivalent. So if I can quantify either of the components, I can ultimately quantify their balanced out original force, the force normal or the force of friction. That's where I'm going to use that angle that we have over here as a way for us to try to figure out what the components' magnitudes should be. If we look at that that 30 degrees right there. That's 30 degrees with what we would consider would be perfectly horizontal. Looking at it like this, that would look like a right triangle, where it would form a 90 degrees with our original force of gravity on this side, and then that would give us a 30, 60, 90 triangle. However, if we treat it like this implies that the force of gravity, that original force, would not be the hypotenuse of this triangle. But we know that the original force should be larger than either of the two components, because the components are part of the original. So we would need to rearrange this triangle to show a different way of representing it. But setting up this way is useful to identify that 60-degree angle. So I'll erase that arrow. What we need to do is set up that force of gravity as its hypotenuse for its own triangle. This right here that I'm drawing in red could be the force of gravity horizontally. That does align with that component force we have. And then this other one that I'm drawing that would form that 90 degrees with the force of gravity horizontal is the force of gravity vertical. This way it looks like a 90-degree triangle. Once again, another 30, 60, 90 triangle. But the way it's drawn this time is with our force of gravity as the hypotenuse. I'm going to redraw this to make it even easier for us to see at the top of the screen. This right here is the original force of gravity that we have already quantified as 98 newtons. This right here is going to be our force of gravity dash x that we don't currently know what the magnitude is going to be. And this part right here is going to be our force of gravity dash y, which we also don't know what it's going to be. So, we do know the angles that we have here. We know that the x and the y components fall on the x and the y axis, so they should be 90 degrees to each other. And by looking at that 30 degrees we were given in the problem, we were able to identify that the angle between the ramp and the original force of gravity is 60 degrees, which would correspond with the angle between the horizontal component of force of gravity and the original force of gravity. We could say that the angle between the force of gravity and the y-axis is 30 degrees if we so chose, but I'm just going to leave it like this. It's important for us to be able to identify this the way it is, because now that we have an angle and the length of one of these sides, we can use trigonometry in order to identify the lengths of the other sides. So, if we have it this way, I'm going to first start off by identifying the horizontal component. That is going to be our adjacent side of our triangle. It's the adjacent side because our angle is right here, and this is the side of the triangle that is adjacent to it. So that means that I can use the cosine function because I know the angle, I know the hypotenuse, and I'm trying to find the adjacent side. So if I start off with cosine of our angle is equal to our adjacent side times our hypotenuse, I can rearrange that to get it so that way our adjacent side is equal to our hypotenuse times the cosine of our angle. And then when I start to plug in what the adjacent and hypotenuse really means, it makes it really easy for me to already have my horizontal component of gravity that's equal to our force of gravity times cosine of that angle. This way, I can end up using this same equation for any situation that I'm looking at where I have components of the force of gravity, regardless of the magnitude of any of these forces or the angle that it's actually forming. It just saves me some steps if later on I want to look at a very similar problem, but maybe just changing the angle or the mass of the box. But to quantify this, force gravity dash x is equal to the 98 newtons, that was our force of gravity, times cosine of this 60-degree angle. So if I were to plug that into a calculator, what I would end up getting would be my values right here, and it should end up being 49 newtons. If you end up plugging this into your calculator, following along with me, and get a different value, what that may indicate is that your calculator is in radians instead of degrees. Make sure that you change your mode of your calculator so that way it is in degrees when we're working with these degrees. So right now, that's going to be how we quantify the force gravity dash x. So 49 newtons of force pointing down the ramp. That is balanced out by 49 newtons of force pointing up the ramp, that force of friction. So we've now quantified the original force of gravity, the component force gravity dash x, and then we were able to use the first law of motion to show that that horizontal component of gravity is balanced out by the force of friction in order to quantify the force of friction. Now that just leaves our force of gravity dash y. The force of gravity dash y is on this side. That is opposite to the angle. So that means that we can use our sine function. Actually, at this point, seeing as we know the amount of the length of the adjacent side, we even could use the tangent if we really cared to. But I'm going to go with the sine side. So that's going to be sine of our angle is equal to our opposite side over the hypotenuse. Just like I did previously, I can rearrange this to get the opposite side by itself, as is equal to the hypotenuse times sine of our angle. The opposite side is the vertical component of gravity. The hypotenuse is the original force of gravity, and sine of that angle is still consistent. So my force of gravity dash y is equal to that 98 newtons of force times sine of 60 degrees. When I plug that into a calculator, I get 84.87 newtons. That's going to be this quantity of force that is perpendicular to the ramp pointing down. That is balanced out by that normal force on the box by the ramp pointing up, 84.87 newtons. So right now we have quantified, no, that last one did not work out super well. We have quantified every single force on this force diagram. We have started off by drawing that qualitative force diagram. Then we ended up using our equivalencies that were supported by our sum of the forces equation in order to relate the magnitudes of our component forces to the other forces in this problem. We were able to use our trigonometric relations and an angle that we knew in order to quantify those components. And ultimately, this all started off with our first way to quantify a force, the force of gravity equation for the force of gravity on Earth.